You are sitting in a room that feels stable. The floor holds you. The walls remain fixed. Light travels in straight lines from objects to your eyes. Time appears to move forward at a steady pace. You assume that the numbers describing the universe beyond this room behave with similar consistency. Distance, speed, temperature, mass. You expect that when measured carefully enough, they align into a coherent picture. They do not. Across cosmology, independent measurements confirm their own internal logic. The expansion rate of the universe can be calculated from the early afterglow of the Big Bang. It can also be measured from exploding stars in nearby galaxies. Both methods are precise, both are repeated, both are refined, and both produce answers that disagree. The discrepancy is not large enough to dismiss as error. It is not dramatic enough to feel catastrophic. It is small, persistent, and resistant to correction. The numbers match themselves. They do not match each other. Nothing about this conflict is speculative. It emerges from telescopes, satellites, and equations that already define modern cosmology. The models remain elegant, the data remain clean. Yet when placed together, the structure they form does not fully close. The question is not whether the universe is expanding. It is not whether the measurements are real. The question is why two equally trusted methods of measuring the same reality refuse to converge on the same answer. What happens when the universe is internally consistent but globally incompatible? The assumption of agreement. You assume that reality, when measured correctly, will agree with itself. If two rulers measure the same table, you expect the same length. In cosmology, however, two independent rulers are applied to the universe's expansion. One ruler is embedded in the relic radiation from the early universe. The other is constructed from distant supernova and galaxy distances. Each ruler is calibrated carefully. Each produces stable results. Yet their measurements diverge in a way that cannot be ignored. The first ruler does not measure the present directly. It measures a pattern, frozen into the cosmic microwave background, the faint afterglow left when the universe cooled enough for light to travel freely. Within that radiation are temperature variations smaller than 1 part in 100,000. These fluctuations encode information about the density of matter, the balance of radiation, and the geometry of space at that early time. When you apply the equations of general relativity to that pattern, you can project forward. You can infer how fast the universe should be expanding today. This method is indirect, but it is not vague. Satellites have mapped this background radiation across the entire sky with extraordinary precision. The statistical uncertainties are small. The physical assumptions are well tested in other contexts. The result is a specific number for the Hubble constant, the present expansion rate of space. It is not an estimate in the casual sense. It is a tightly constrained outcome of a model that fits early universe data with remarkable success. The second ruler avoids projection. It remains in the relatively nearby universe. You measure distances to galaxies using standard candles, objects whose intrinsic brightness can be determined. By comparing how bright they appear to how bright they are known to be, you calculate distance. Then you measure how much their light has been redshifted by cosmic expansion. Distance and redshift together reveal how fast space is expanding locally. This method builds upward in steps. Parallax anchors nearby stars. Cepheid variables extend the scale outward. Type 1, a supernovae, carry it across intergalactic space. Each layer is cross-checked. Independent teams refine calibration. The uncertainties narrow. The result is another precise value for the same cosmic parameter. If both rulers are measuring the same universe, under the same physical laws, the results should converge. They do not. The difference is not dramatic in everyday terms. It is a matter of several kilometers per second per megaparsec. But when that rate is applied across billions of light years, the discrepancy compounds. It shifts the inferred age of the universe by hundreds of millions of years. It alters the timeline for galaxy formation. It subtly reshapes the history you reconstruct. You might suspect error in one method, yet each is internally consistent. The early universe model explains not only the background radiation, but also the abundance of light elements and the distribution of large-scale structure. The local distance ladder aligns with multiple independent indicators, including gravitational lensing time delays and surface brightness fluctuations. Systematic errors have been hunted repeatedly. None large enough to close the gap have been found. Agreement is not failing because of noise. It is failing despite precision. You are left with two coherent narratives of expansion. One begins 13.8 billion years ago and evolves forward. The other measures the current state directly and works backward. Both rely on general relativity. Both rely on well-tested atomic physics. Both use light as a messenger across time. The assumption that reality agrees with itself remains unbroken in principle. The laws of physics appear uniform. The equations remain stable. What fractures is the bridge between epochs. If the universe expanded differently in its earliest moments than the model assumes, the background radiation would encode that difference. If it behaves differently now than projected, local measurements would reveal it. Each method insists on its own internal logic. The tension does not imply chaos. It implies incompleteness. The two rulers, applied carefully to the same cosmic fabric, refuse to produce the same length. And you are forced to consider the possibility that the disagreement is not in the tools, but in the assumptions connecting them. Readingeth into the afterglow. The oldest light in the universe, the cosmic microwave background, preserves a snapshot of conditions 380,000 years after the Big Bang. Tiny fluctuations in that radiation encode the density, geometry, and expansion rate of the early cosmos. From this imprint, a value for today's expansion rate is extrapolated using well-tested physics. The calculation is internally precise. The uncertainty margins are narrow. But this value does not match what is measured in the nearby universe. To understand why this radiation carries so much information, you begin with a simple premise. In its earliest state, the universe was not transparent. Matter existed as a hot plasma of electrons and protons. Photons scattered constantly, unable to travel freely. The universe behaved less like empty space and more like a dense, luminous fog. Within that plasma, pressure and gravity competed. Regions slightly denser than average collapsed inward under gravity. Radiation pressure pushed outward. These opposing forces created oscillations, waves moving through the primordial medium. When the universe cooled enough for electrons and protons to combine into neutral atoms, light decoupled from matter. The fog lifted. The photons released at that moment have been traveling ever since. What you observe today is that ancient light, stretched by cosmic expansion into microwave wavelengths. The temperature variations across the sky are small, but they are not random. They are the frozen pattern of those early oscillations. The spacing of these fluctuations forms a kind of standard ruler. It reflects how far sound waves traveled in the early universe before light was released. That distance depends on the density of matter, the amount of radiation, and the overall curvature of space. By measuring the angular size of these patterns on the sky, you can infer the geometry of the universe and the rate at which it expanded during its first moments. This is not a speculative reconstruction. Satellites have mapped this background radiation with full sky coverage and high resolution. The statistical analysis is exhaustive. The result is a cosmological model defined by a small set of parameters: ordinary matter, dark energy, and the initial conditions of expansion. When these parameters are adjusted to fit the microwave background, the fit is extraordinarily tight. Residuals are minimal. Independent observations of large-scale structure reinforce the same parameter set. From this early snapshot, you project forward. You allow gravity to amplify small fluctuations into galaxies and clusters. You allow dark energy to accelerate expansion at late times. You let the equations evolve for 13.8 billion years. The outcome is a present-day expansion rate with a precision of a few percent or better. What makes this method compelling is its coherence. It does not measure the expansion rate directly today. It measures the early universe and relies on the continuity of physical law. If general relativity holds, if particle physics behaves consistently, if no unseen component intervenes, then the extrapolation is justified. Yet when compared to local measurements, the inferred expansion rate is lower. The universe, according to its own afterglow, should be expanding more slowly than nearby supernovae suggest. You might suspect that extrapolating across billions of years introduces fragility, but the same model that yields the expansion rate also predicts the relative abundances of hydrogen and helium formed in the first minutes. It predicts the large-scale clustering of galaxies. It predicts the flatness of space within tight limits. Each of these predictions has been tested. Each aligns with observation. The afterglow does not appear confused. It presents a consistent narrative of the early cosmos. Its parameters interlock, adjust one significantly, and the entire pattern distorts. This is what makes the mismatch unsettling. The cosmic microwave background is not ambiguous data. It is one of the most precisely measured data sets in all of science. Its interpretation rests on equations that govern planetary orbits and gravitational lensing with equal success. If the expansion rate it implies is incorrect, then either the extrapolation across cosmic time hides a subtle flaw, or some ingredient in the model is incomplete. But nothing in the radiation itself signals instability. It is smooth, coherent, and mathematically obedient. You are left with a relic light that tells a clear story about the beginning and the present universe that appears to be expanding faster than that story allows. The afterglow is silent about the discrepancy. It simply encodes its numbers, and indifferent to whether they agree with what you measured now, measuring the present directly. Instead of looking backward, You can measure expansion directly. Observe distant supernovae, track how their light stretches, calibrate their intrinsic brightness using closer stellar markers. This method constructs a distance ladder from the local universe outward. The result is another value for the expansion rate. It is measured independently of the early universe model. It is equally precise, and it is consistently higher. The logic appears straightforward. If space is expanding, light traveling through it will stretch. The greater the distance, the more stretching occurs. This stretching shifts light toward longer redder wavelengths. The redshift is measurable with spectroscopy. It is not inferred. It is recorded as displays spectral lines in the light of distant galaxies. Redshift alone does not give you expansion. It gives you velocity relative to distance. To convert that velocity into a rate, you must know how far away the object is. Distance in astronomy cannot be measured with a tape measure. It must be inferred from brightness. This is where standard candles enter. Certain objects in the universe have predictable intrinsic luminosities. If you know how bright something truly is, and you observe how bright it appears, you can calculate how far away it must be. The inverse square law governs this relationship. Double the distance, and the brightness drops by a factor of 4. Type 1. A supernovae serve as the most powerful of these candles. They are thermonuclear explosions of white dwarf stars that reach nearly uniform peak brightness. While not perfectly identical, their variations can be standardized through light curve analysis. Once corrected, they become reliable distance indicators across hundreds of millions of light years. But supernovae cannot calibrate themselves. To know their true brightness, you must anchor them to closer distance measurements. This creates the distance ladder. At the base is parallax, the slight shift in a star's position as Earth orbits the Sun. Parallax provides geometric distance for nearby stars. Among those stars are Cepheid variables, pulsating stars whose period of brightness variation correlates with intrinsic luminosity. Measure the period, and you know the true brightness. Use Cepheids in galaxies that also host supernovae, Dioc, and you transfer that calibration outward. Each rung depends on the stability of the previous one. Parallax is measured with space-based observatories capable of detecting shifts smaller than a milliarc second. Cepheid behavior has been studied for over a century. Supernova light curves are analyzed with detailed models. Independent research groups cross-check calibration methods. Statistical uncertainties are reduced. When redshift is plotted against these measured distances, a slope emerges. That slope is the present-day expansion rate, and it consistently yields a value higher than the one derived from the cosmic microwave background. The difference is not random. It remains across different datasets, different telescopes, and different analysis techniques. Even alternative calibration strategies, such as using red giant branch stars instead of Cepheids, produce results that remain elevated relative to the early universe prediction. You might question whether local structure biases the measurement. Perhaps our region of space is atypical, but large surveys map galaxy distributions across wide volumes. The local universe does not appear underdense or anomalous enough to account for the discrepancy. The effect persists beyond immediate cosmic neighborhood scales. Unlike the early universe method, this approach does not assume a model of primordial physics. it does not extrapolate across billions of years. It measures the present state of expansion directly, using observable objects whose light is arriving now. That independence is critical. If both methods relied on the same assumptions, their agreement would be less meaningful. But they begin from different epochs and different data. One reads a fossil imprint, the other observes ongoing motion, and yet they do not converge. The latter stands intact. The calibrations hold. The redshifts are clear. The slope remains steep. If the universe is expanding faster today than its early radiation implies, then something altered the trajectory between then and now. Or the connection between early conditions and late behavior is not as complete as assumed. You measure the present directly. The numbers respond. They are stable, reproducible, and incompatible with the past you reconstructed from ancient light. A difference too large to ignore. The gap between these two expansion rates is only a few kilometers per second per megaparsec. On human scales, it is negligible. On cosmic scales, it compounds across billions of light years. The statistical significance has grown with each refinement. The discrepancy now exceeds what random error should produce. The numbers are not fluctuating toward agreement. They are stabilizing apart. If the universe expands at roughly 67 kilometers per second per megaparsec, according to the early universe inference, and roughly 73 according to local measurements, the difference appears modest. The units themselves obscure intuition. A megaparsec is about 3.26 million light-years. The rate describes how much faster two galaxies recede for every additional megaparsec between them. Over a single megaparsec, the gap between 67 and 73 is 6 kilometers per second. Over 1,000 megaparsecs, it becomes 6,000 kilometers per second. Across the observable universe, the cumulative divergence reshapes scale. This is not a rounding error. Expansion rate determines the inferred age of the universe. A slower rate implies more time has passed since the Big Bang. A faster rate compresses that timeline. The difference shifts cosmic history by hundreds of millions of years. It alters when the first stars formed, when galaxies assembled, how long structures had to evolve. In statistics, disagreement is expected at some level. Measurements carry uncertainty. If two independent experiments differ slightly, but within their margins of error, no tension is declared. What makes this case unusual is that the error bars no longer overlap in a comfortable way. As data improves, the margins shrink. Instead of converging within a shared range, the central values remain separated. The statistical significance of the discrepancy has crossed thresholds that, in other fields, would suggest new physics or systematic oversight. 5 sigma is often treated as a discovery standard in particle physics. The expansion tension approaches comparable confidence depending on dataset combinations. It is not a fleeting anomaly from a single survey. It persists across multiple observational campaigns. You might expect that with time, hidden biases would be uncovered. Perhaps dust obscures supernova brightness slightly more than assumed. Perhaps early universe modeling contains subtle parameter degeneracies. Teams have investigated these possibilities. Alternative calibrations have been implemented. Independent instruments have repeated measurements. The results shift slightly, but the separation remains. The numbers are not drifting randomly, they are clustering into 2 camps, one centered on the lower value derived from the cosmic microwave background and baryon acoustic oscillations, the other anchored to the higher value from supernovae, Cepheids, red giant stars, and gravitational lensing time delays. When this agreement is small and unstable, you can wait for resolution. When this agreement is stable and growing in statistical weight, waiting becomes a strategy without guarantee. What complicates the situation further is that both values are internally consistent within their frameworks. The early universe value fits a coherent model that explains multiple independent phenomena. The local value arises from a chain of empirical measurements rooted in geometry and stellar physics. Neither appears careless. Neither shows obvious internal contradiction. This leaves you in an uncomfortable position. If you adjust the early universe model to raise its predicted expansion rate, you risk disturbing the delicate agreement with background radiation patterns and large-scale structure. If you lower the local measurement through recalibration, you must account for why independent distance indicators converge on similar high values. The gap is narrow in absolute terms, but profound in implication. Cosmology rests on the assumption that a single set of parameters describes the entire history of the universe. A persistent mismatch in the expansion rate challenges that assumption directly. You are not observing chaos, you are observing precision without unity. Two measurements of the same cosmic property disagree beyond what chance allows. The more carefully you measure, the less room remains to attribute the difference to error. The numbers do not oscillate toward reconciliation. They settle into their positions, and the space between them becomes harder to dismiss. Precision without convergence. Modern instruments reduce uncertainty to fractions of a percent. Satellites map background radiation with extraordinary sensitivity. Space telescopes measure stellar distances with unprecedented clarity. Yet as precision increases, convergence does not follow. Instead, clarity sharpens the divide. Measurement improves. Agreement does not. In most areas of science, refinement brings resolution. Early measurements disagree widely. Instruments improve. Methods are corrected. The values begin to cluster. Eventually, a stable number emerges. The expectation is not blind optimism. It is based on experience. Precision historically dissolves tension. In cosmology, the opposite pattern is emerging. The cosmic microwave background has been mapped across the full sky with angular resolution fine enough to resolve temperature fluctuations at minute scales. Statistical noise has been suppressed through repeated observation. Foreground contamination from our own galaxy has been modeled and subtracted. Independent teams analyzing the same data recover nearly identical parameter values. The expansion rate inferred from this early snapshot is not drifting unpredictably. It is locked in by multiple interdependent features of the radiation pattern. At the same time, local measurements have undergone their own tightening. Parallax distances are now measured from space with micro-arcsecond precision, reducing geometric uncertainty to unprecedented levels. Cepheid variables are observed in multiple wavelengths to correct for dust and metallicity effects. Supernova light curves are standardized with refined empirical relations derived from large samples. Each potential systematic bias is isolated, modeled, and constrained. If hidden error were responsible for the tension, shrinking uncertainties should expose it. Instead, smaller error bars harden the separation. The central values remain stable, while confidence in them increases. This creates an unusual condition. The disagreement is no longer blurred by measurement noise. It stands in clear focus. Two highly precise methods yield two distinct expansion rates. Neither exhibits large internal scatter. Neither displays instability under methodological variation. Precision has removed ambiguity, but not conflict. You might expect that cross-checks using entirely different phenomena would break the tie. Gravitational lensing time delays measure cosmic distances through the bending of light by massive galaxies. Surface brightness fluctuations use the statistical variation in stellar populations to estimate distance. The tip of the red giant branch provides an alternative stellar calibration independent of Cepheids. Many of these methods lean toward a higher expansion value. Some align more closely with the lower value. None bridge the gap decisively. What emerges is not chaos, but bifurcation. Observations cluster into two internally consistent regimes. The early universe framework anchored in primordial radiation. The late universe framework grounded in direct distance measurements. The precision itself introduces rigidity. When uncertainties were large, theoretical adjustments had room to maneuver. Now, small changes in parameters produce measurable distortions elsewhere. Adjusting dark energy behavior slightly to reconcile expansion rates may disrupt the fit to background radiation peaks. Introducing additional early radiation alters nucleosynthesis predictions. Every correction propagates. This rigidity is not a flaw, it is the result of a model that successfully integrates diverse phenomena under a unified mathematical structure. But it also means that small discrepancies cannot be absorbed quietly. They strain the entire framework. You are confronted with an unexpected pattern. Improved measurement does not heal division, it clarifies it. The better you see, the more sharply the numbers diverge. There is no dramatic collapse. No equations fail catastrophically. Gravity still governs planetary motion. Atomic transitions remain stable. The large-scale structure of galaxies matches simulations within accepted margins. The model continues to function across most tests, but at the level of a single parameter, the rate at which space expands, the universe presents two answers. Precision was expected to converge them. Instead, it has made their separation undeniable. The model that almost works. The standard cosmological model describes a universe composed of ordinary matter, and dark energy. It explains structure formation, background radiation, and large-scale distribution of galaxies. When fitted to early universe data, it performs exceptionally well. When applied to late-time measurements, tension appears. The model is not collapsing, it is straining. You begin with a framework often called a lambda C, D, M. Lambda represents dark energy, a constant energy density filling space. CDM stands for cold dark matter, a non-luminous substance that interacts gravitationally but not electromagnetically. Add ordinary matter and radiation, and you have a compact set of ingredients governed by general relativity. From these components, the large-scale behavior of the universe is calculated. The strength of this model lies in its economy. With only a handful of parameters, it reproduces an extraordinary range of observations. The pattern of fluctuations in the cosmic microwave background aligns with its predictions. The relative heights of acoustic peaks match the inferred ratios of matter and radiation. The abundance of light elements formed in the first minutes agrees with its early expansion rate. The distribution of galaxies across billions of light years follows the growth of dark matter halos seeded by primordial density variations. When simulations evolve this model forward in time, filamentary structures emerge. Galaxies cluster along invisible scaffolding formed by dark matter. Voids expand. Clusters merge. The statistical properties of these structures correspond closely to what telescopes observe. The agreement is not approximate in a casual sense. It is quantitative. This is why the expansion tension does not trigger immediate rejection of the model. The framework works too well across too many domains. It connects phenomena separated by scale, energy, and epoch. Remove dark matter, and galaxies cannot form as observed. Remove dark energy, and the late-time acceleration of expansion disappears. Alter the balance of components, and the microwave background pattern shifts out of alignment. Yet when the model is anchored to early universe data, it predicts a present-day expansion rate lower than what direct measurements suggest. The tension does not arise from a failure of fit in the early epoch. It arises when that early fit is extrapolated forward. The model assumes that dark energy behaves as a cosmological constant, unchanging in time. It assumes dark matter is cold and collisionless. It assumes general relativity applies uniformly across cosmic scales. Within these assumptions, the universe evolves smoothly from its hot beginning to its current accelerated state. If any of these assumptions are incomplete, small deviations could alter the expansion history subtly but cumulatively. A slight change in dark energy behavior at early times could shift the inferred Hubble constant. A minor interaction within the dark sector might modify structure growth without dramatically altering the microwave background. But the model's interconnectedness limits freedom. Adjust one parameter and others compensate. Increase early radiation density to raise the expansion rate, and you disturb the spazzing of acoustic peaks. Modify dark energy's equation of state, and you affect supernova distance fits and baryon acoustic oscillations. Each alteration must pass multiple observational filters simultaneously. This is the strain. The model bends but resists breaking. It can absorb small modifications, but not arbitrary ones. Its success across independent datasets acts as both strength and constraint. You are not observing a theory in crisis, you are observing a theory under pressure. The discrepancy in expansion rate does not invalidate the cosmic microwave background interpretation. It does not erase the evidence for dark matter. It does not overturn gravitational lensing measurements. It introduces a localized fracture in an otherwise coherent structure. The discomfort lies in proximity. The model nearly works everywhere. It fails only in reconciling two precise measurements of the same parameter. The failure is subtle enough to question. It is persistent enough to resist dismissal. You are left with a cosmology that explains almost everything with minimal ingredients, yet hesitates at a single junction between past and present. The strain does not tear the framework apart. It simply reminds you that near completeness is not completeness. Dark matter's silent role. Galaxies rotate too quickly to be held together by visible matter alone. The existence of dark matter resolves this discrepancy. Its gravitational influence shapes cosmic structure. It is invisible, but measurable through its effects. Yet adjusting dark matter properties within known constraints does not erase the expansion tension. The unseen mass explains some inconsistencies, not this one. When you measure how stars orbit within spiral galaxies, their speeds remain high, even far from the galactic center. According to Newtonian gravity and general relativity, orbital velocity should decrease as distance from visible mass increases. It does not. The outer regions move too fast. If only luminous matter were present, galaxies would disperse over cosmic time. Dark matter provides the missing gravitational pull. It does not emit light. It does not absorb or reflect radiation in any measurable way, but its mass curves space-time. Through gravitational lensing, you observe light bending around regions where little visible matter exists. Through galaxy cluster dynamics, you infer mass far exceeding what stars and gas account for. Independent lines of evidence converge on the same conclusion. Most matter in the universe is dark. In the standard cosmological model, dark matter is cold and collisionless. Cold means its particles moved slowly in the early universe, allowing small density fluctuations to collapse efficiently. Collisionless means it interacts primarily through gravity. These properties are not arbitrary. They are required to reproduce the observed large-scale structure. Simulations using cold dark matter generate filamentary networks and halo distributions consistent with galaxy surveys. Dark matter also plays a central role in interpreting the cosmic microwave background. The heights and spacing of acoustic peaks depend on the relative densities of baryonic matter and dark matter. The early universe expansion rate is influenced by how much total matter is present. Adjust the dark matter density significantly, and the background radiation pattern shifts in measurable ways. Given its influence, you might expect that modifying dark matter properties could reconcile the expansion discrepancy. Perhaps if dark matter decayed slowly over time, or interacted weakly with radiation in the early universe, thus it could alter the inferred Hubble constant. Proposals along these lines have been examined. If dark matter possessed additional interactions, it could change the sound horizon scale imprinted in the cosmic microwave background. That might shift the extrapolated expansion rate upward, but such modifications are tightly constrained. Too much interaction distorts the microwave background spectrum beyond observed limits. Too little produces negligible effect. Similarly, if dark matter were warmer rather than cold, small-scale structure formation would be suppressed. Dwarf galaxy counts and Lyman alpha forest observations restrict how warm it can be. These independent datasets limit how far dark matter properties can deviate from the cold, collisionless assumption without creating new inconsistencies. The expansion tension therefore cannot be resolved by freely adjusting dark matter density or behavior within currently allowed bounds. Its gravitational role remains essential, but it does not provide sufficient flexibility to bridge the measured gap. This reveals something structural about the problem. The discrepancy is not simply a matter of adding more unseen mass. The matter content of the universe is already tightly constrained by multiple observations. Dark matter accounts for approximately 5 times as much mass as ordinary matter. And that ratio emerges consistently across methods. If you attempt to increase dark matter density to influence expansion, you alter galaxy clustering statistics and lensing measurements. If you reduce it, you weaken structure formation below observed levels. The model balances delicately. Dark matter solves one set of numerical mismatches. It explains why galaxies rotate as they do and why clusters remain bound. It aligns gravitational lensing with observed luminous mass. It fits seamlessly into the early universe framework. But when confronted with the expansion tension, dark matter remains silent. Its presence is required. Its properties are constrained. And within those constraints, it does not reconcile the two expansion rates. You are left with a component that accounts for most of the universe's mass, shapes its structure, and yet offers no obvious path toward resolving the discrepancy between early and late measurements. The unseen mass exerts gravitational influence everywhere, but it does not pull the numbers into agreement. The dark energy and accelerated expansion. Observations of distant supernovae revealed that expansion is accelerating. Dark energy was introduced as a uniform energy permeating space. It fits supernova data, it fits background radiation data, but small changes in its behavior could alter expansion history. The problem is that current measurements restrict how much it can vary. Within those limits, the tension persists. When distant type 1, a supernova, were first measured at the end of the 20th century, they appeared dimmer than expected. Given their redshift, they should have been closer if expansion were slowing under gravity alone. Instead, they are farther away. The only consistent interpretation within general relativity was that cosmic expansion is not decelerating, it is accelerating. Acceleration requires a source. Matter, whether ordinary or dark, produces gravitational attraction. To generate acceleration, the universe must contain a component with effectively negative pressure. In the equations of general relativity, pressure contributes to gravitational behavior. A sufficiently negative pressure causes space-time to expand more rapidly over time. Dark energy is the name given to this component. In the simplest version of the cosmological model, it is represented by a constant term, often associated with vacuum energy. Its density remains uniform as space expands. As matter thins out over time, dark energy becomes dominant. The transition from matter-dominated deceleration to dark energy-driven acceleration occurs several billion years into cosmic history. This simple description aligns with multiple datasets. The brightness redshift relationship of supernovae follows the curve predicted by a universe with approximately 70% dark energy. The cosmic microwave background, when analyzed under the same model, is consistent with a spatially flat universe, whose total energy density includes this dominant component. Large-scale galaxy clustering also reflects the influence of accelerated expansion on structure growth. Given its role in shaping expansion history, dark energy appears to be a natural candidate for resolving the Hubble tension. If its properties differed slightly from a pure cosmological constant, the expansion rate today could shift relative to the early universe extrapolation. One way to describe dark energy behavior is through its equation of state parameter, commonly denoted as W, which relates pressure to energy density. For a cosmological constant, W equals -1. If W deviates from this value, even slightly, the expansion history changes. In principle, a time-varying dark energy component could alter the relationship between early and late expansion. However, observational constraints are tight. Supernova surveys across a wide range of redshifts measure how expansion evolved over billions of years. Baryon acoustic oscillation data provides an independent distance scale at intermediate epochs. Combined with cosmic microwave background measurements, these observations restrict W to be very close to -1, with little room for significant evolution. If dark energy varied strongly in the early universe to raise the inferred Hubble constant, it would leave detectable imprints in the background radiation pattern and in the growth rate of cosmic structures. Those imprints are not observed at the required magnitude. The allowed deviations are small. Within those small margins, the expansion tension remains. You could propose a more complex dark energy model with additional parameters. Perhaps an early dark energy component briefly contributed a few % of the total density before fading. Such models are explored seriously, yet they must tread a narrow path, large enough to influence the sound horizon scale in the cosmic microwave background, small enough to avoid distorting peak structures beyond observed limits. The result is not impossibility, but constraint. Dark energy cannot be adjusted freely. It is measured indirectly through its gravitational effects, and those effects are cross-checked by multiple independent observations spanning cosmic time. Acceleration is real. Its magnitude is measured. Its influence is embedded in both early and late data, but within the observational boundaries currently established. Modifying dark energy behavior does not easily reconcile the two expansion rates. You are left with a component that dominates the universe's energy budget, drives its accelerated expansion, and yet offers only limited flexibility. Dark energy shapes cosmic history profoundly, but within the precision of current measurements, it does not pull the divergent numbers into alignment. Early adjustments, late consequences. One possibility is that the early universe contained additional energy components. Slight changes in early conditions could ripple forward into present expansion rates. Yet such modifications would alter the background radiation patterns we already measure with precision. Any adjustment must solve one problem without creating another. So far, no proposal satisfies both. The logic is straightforward. The expansion rate, inferred from the cosmic microwave background, depends on the size of the sound horizon at the time light decoupled from matter. That sound horizon is the maximum distance acoustic waves could travel through the primordial plasma before photons began moving freely. Its scale is determined by how fast the universe was expanding and what forms of energy were present at that time. If the early universe expanded slightly faster than assumed in the standard model, the sound horizon would be smaller. A smaller sound horizon, when interpreted through current observations, could raise the inferred present-day expansion rate. In principle, this adjustment might bring early and late measurements into alignment. To accelerate early expansion, you must introduce additional energy density at that epoch. This energy must behave differently from ordinary matter and radiation. It must contribute enough to alter the expansion rate before recombination, but diminish sufficiently afterward to avoid dominating later cosmic evolution. One class of proposals introduces what is called early dark energy. In these models, a small fraction of the total energy density briefly increases before recombination, and then dilutes or decays. The timing is critical. The contribution must peak at just the right moment to reduce the sound horizon without significantly distorting other features of the cosmic microwave background. The difficulty lies in the interconnectedness of observables. The microwave background is not characterized by a single number. It contains a detailed pattern of acoustic peaks. Their positions, heights, and relative spacing encode information about baryon density, dark matter density, expansion history, and radiation content. Altering the early expansion rate shifts these peaks. Compensating for that shift requires adjusting other parameters. Those adjustments propagate through the model. For example, adding additional relativistic particles in the early universe, sometimes described as increasing the effective number of neutrino species, changes the expansion rate and the damping tail of the microwave background spectrum. But measurements of that spectrum tightly constrain how many such particles can exist. The allowed variation is small. Too much additional radiation would conflict with the observed anisotropy pattern. Big Bang nucleosynthesis adds another constraint. The abundances of light elements such as helium and deuterium depend sensitively on the expansion rate during the first few minutes after the Big Bang. Increase early energy density too much, and the predicted element ratios diverge from what is measured in ancient gas clouds. Large-scale structure provides a further check. The growth rate of density fluctuations depends on how the universe expanded over time. Early modifications influence later structure formation. Galaxy clustering, statistics, and weak gravitational lensing measurements limit how much deviation is permissible without producing inconsistencies elsewhere. This creates a narrow corridor of possibility, and any additional early component must be strong enough to shift the inferred Hubble constant by several percent. At the same time, it must remain subtle enough to preserve the detailed agreement between the standard model and multiple datasets. Several models have approached partial success. They reduce the tension somewhat, but rarely eliminate it entirely. Often, resolving the expansion discrepancy introduces mild inconsistencies in other observables. The improvement in one parameter comes at the expense of fit quality in another. You are confronted with a system in which the early universe is not a blank slate. It is tightly constrained by relic radiation, elemental abundances, and structure growth. Small early adjustments echo forward across billions of years. The universe carries memory of its initial conditions with high fidelity. To solve the present discrepancy by modifying the past requires altering that memory without leaving detectable scars. So far, every attempt leaves some trace. The tension may shrink, but it does not vanish without cost. The possibility remains that an undiscovered early component exists, but the space in which it can operate is limited. You are not free to rewrite the beginning without rewriting everything that followed. The ladder of distance. The cosmic distance ladder depends on stepwise calibration. Parallax measures nearby stars. Cepheid variables extend farther. Supernovae reach across galaxies. Each rung introduces potential systematic error. Extensive cross-checking reduces uncertainty. Independent teams reproduce results. The ladder remains standing. The higher expansion rate persists. Distance is the most difficult quantity to measure in astronomy. You cannot travel to a galaxy and return with a direct reading. You must infer distance from geometry and light. The ladder approach accepts this limitation and builds outward in controlled stages. At the foundation is parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the more distant background. The angle of that shift, though minute, is measurable with space-based observatories. Geometry alone converts that angle into distance. No astrophysical assumptions are required. This base rung is anchored in trigonometry. From parallax distances, you calibrate the intrinsic brightness of certain variable stars, most notably Cepheids. Cepheids pulsate with a regular period that correlates tightly with their true luminosity. Measure the period of variation, and you infer how bright the star actually is. Compare that intrinsic brightness to its observed brightness, and you determine its distance. Cepheids are luminous enough to be observed in nearby galaxies, extending the ladder beyond the reach of parallax alone. In galaxies that host both Cepheids and Type 1, a supernovae, another transfer occurs. Once the distance to the host galaxy is established through Cepheids, the supernova within it can be calibrated. Type 1, a supernovae are far brighter than Cepheids. They can be seen across vast cosmological distances. With their intrinsic brightness standardized through empirical light curve relations, they become markers across the observable universe. Each rung depends on the stability of the previous one. A bias in parallax would propagate upward. An unrecognized metallicity effect in Cepheids could alter supernova calibration. Dust absorption could dim light and mimic greater distance. These are not overlooked possibilities. They are studied intensively. Parallax measurements are repeated and refined using different instruments and analysis pipelines. Cepheid observations are conducted in multiple wavelengths to correct for dust and environmental effects. Alternative calibrators, such as the tip of the red giant branch, provide an independent route to anchor supernova brightness. Surface brightness, fluctuations, and the Maser distances offer additional cross-checks. The objective is not simply to obtain a number, but to isolate and constrain every plausible source of systematic error. When multiple independent approaches converge on similar distances, confidence increases. The higher value of the Hubble constant derived from these local measurements does not rest on a single fragile assumption. It rests on a network of interlocking calibrations. Critics have examined whether local cosmic variance could bias results. If a region of the universe were unusually underdense, nearby galaxies might recede faster relative to the cosmic average. Large-scale surveys, however, indicate that while structure exists on many scales, there is no evidence of a void large enough to account for the full discrepancy. The ladder is not perfect. No measurement system is. But imperfections should manifest as scatter or instability. Instead, what you observe is consistency within the ladder itself. Independent research groups, using different telescopes and statistical methods, recover expansion rates clustered near the higher value. This persistence is significant. If the tension were driven primarily by overlooked calibration error, successive refinements should shift the central value substantially. Instead, refinements tighten uncertainty while leaving the central estimate largely intact. The ladder remains structurally sound. Its base is geometric. Its intermediate rungs are astrophysical but repeatedly tested. Its upper reach spans deep cosmic distances through standardized explosions. And at the top of that ladder stands a number that refuses to descend toward the early universe prediction. The framework does not visibly wobble, yet the height it measures remains incompatible with the value derived from the afterglow of the beginning. Independent confirmations. Gravitational lensing offers another approach. Massive objects bend light, encoding information about cosmic expansion. Time delays between lensed images provide distance estimates. These measurements often align more closely with a higher local expansion value. The discrepancy is not isolated to one technique. It echoes across methods. Gravity does not only pull on matter, it bends light. When a massive galaxy lies between you and a more distant quasar, space-time curves around that intervening mass. Light from the quasar travels along multiple paths, arriving at Earth as separate images. These images are not simultaneous, because the light follows paths of different lengths through curved space-time. Variations in the quasar's brightness appear in one image before the other. The delay between those variations is measurable. It depends on two factors: the geometry of the light paths and the rate at which the universe is expanding. If space expands faster, distances between observer, lens, and source scale differently, altering the time delay. By modeling the mass distribution of the lensing galaxy and measuring the time lag precisely, you can infer a quantity known as the time delay distance. From that, the Hubble constant follows. This method does not rely on cathades or supernova calibration. It does not extrapolate from the early universe. It operates at intermediate cosmic distances using general relativity and observed light curves. The inputs are distinct. The systematics are different. Lensing measurements require careful modeling of the lens galaxy's mass profile. Visible stars account for some of the mass. Dark matter contributes the rest. The distribution must be reconstructed from imaging data and stellar velocity dispersion measurements. Small modeling errors could bias results. For that reason, multiple independent groups analyze the same systems using different techniques. Despite these complexities, time delay lensing has produced expansion rates that often lean toward the higher value, consistent with the distance ladder. The uncertainties are larger than those from the cosmic microwave background, but the central values do not naturally converge with the lower early universe estimate. Other lensing-based approaches contribute as well. Strong lensing statistics, weak gravitational lensing surveys in a galaxy cluster, mass reconstructions, all constrained combinations of cosmological parameters that include the expansion rate. While not always decisive on their own, they tend to support a universe whose late-time behavior aligns more comfortably with the higher Hubble constant. This pattern matters because it weakens the argument that the tension arises solely from one fragile chain of calibration. If supernova brightness were misestimated, lensing time delays would not automatically shift in the same direction. If cathode metallicity corrections were flawed, gravitational deflection of quasar light would remain unaffected. Instead, multiple independent probes of distance and geometry appear to cluster in a similar range. They do not agree perfectly with one another. Each carries its own uncertainties, but the echo is present. The higher expansion value is not confined to a single observational ladder. At the same time, some large-scale structure analyses and baryon acoustic oscillation measurements continue to align more closely with the lower value inferred from the cosmic microwave background. The division is not absolute, it is statistical. You are not observing unanimous agreement on either side. You are observing a distribution of methods, many of which independently favor a faster present expansion than the early universe model predicts. Independent confirmation does not eliminate doubt, it redistributes it. If several techniques converge on a higher value, the possibility that all share the same hidden systematic becomes less plausible. The tension broadens from a dispute between two measurements into a network of partial alignments. The universe is being measured from different angles: light bent by gravity, stars pulsing in distant galaxies, explosions marking cosmic distances, relic radiation from the primordial plasma. These are distinct phenomena governed by the same underlying physics, yet when their implications are translated into a single parameter, they do not coalesce cleanly. The discrepancy persists not because one method stands alone, but because it resonates across several. Large-scale structure clues. The distribution of galaxies across vast distances traces the imprint of early sound waves in primordial plasma. This baryon acoustic scale acts as a standard ruler. It links early universe physics to later structure. Measurements from galaxy surveys bridge epochs. They partially favor one side of the tension, but not decisively enough to close it. In the early universe, before light decoupled from matter, pressure waves moved through the hot plasma. These acoustic oscillations were driven by the interplay between gravity pulling matter inward and radiation pressure pushing outward. When recombination occurred and photons began traveling freely, those waves effectively froze in place. The maximum distance they had traveled became imprinted as a characteristic scale in the distribution of matter. That scale did not disappear. As the universe expanded and matter collapsed into galaxies and clusters, the imprint remained as a slight statistical preference for galaxies to be separated by a specific distance. It is subtle. You do not see it by inspecting individual galaxy pairs. It emerges only when millions of galaxies are mapped and their separations analyzed collectively. This preferred separation is known as the baryon acoustic oscillation scale. Because its physical size can be calculated from early universe physics, it functions as a standard ruler embedded in cosmic structure. Measure its apparent size at different redshifts, and you obtain information about how the universe has expanded over time. Large galaxy surveys chart the three-dimensional positions of galaxies across enormous volumes. By comparing the observed acoustic scale to the predicted physical scale derived from the cosmic microwave background, you can infer distances at intermediate epochs. This bridges the gap between the early universe and the present. If the expansion history followed precisely the path predicted by the standard cosmological model, the baryon acoustic oscillation measurements would align seamlessly with both the microwave background inference and the local distance ladder. In practice, they align closely with the early universe prediction when interpreted within that same framework. This alignment strengthens the case for the lower Hubble constant, inferred from primordial radiation. It suggests that the sound horizon scale, measured at recombination, remains consistent with galaxy clustering data, billions of years later. The early imprint appears preserved, yet the interpretation is not entirely independent. The acoustic scale relies on a physical size calibrated by early universe conditions. If those conditions are modified to address the Hubble tension, the ruler itself changes. In that sense, the baryon acoustic oscillations are not a separate measurement of the present expansion rate in the same way supernovae are. They are connected to the same early physics that defines the microwave background inference. Still, they provide a cross-epoch test. They measure how distances evolve with redshift across cosmic time. In doing so, they constrain combinations of parameters, including matter density, dark energy behavior, and curvature. When analyzed jointly with supernova data, they narrow the allowed parameter space further. Some combined analyses show mild shifts toward reconciling values. Others reinforce the separation. The statistical landscape becomes complex. Different survey selections, redshift ranges, and modeling choices produce slightly different outcomes. None erase the tension cleanly. What you observe is partial alignment. Large-scale structure data often supports the lower expansion value when tied to early universe calibration. But when combined with late-time probes, the global fit strains. The standard ruler confirms consistency within its own assumptions. It does not independently resolve the conflict. This is the bridging function of large-scale structure. It connects epochs, but it also transmits the tension between them. The acoustic imprint from the primordial plasma extends forward into galaxy distribution. It carries early universe information across billions of years. And yet, even with this bridge in place, the full set of observations does not settle into a single expansion rate. The standard ruler measures faithfully. The galaxies cluster as expected. The imprint remains visible, but the numbers, once translated into today's expansion, still hesitate between two values. When error shrinks, tension grows. In science, disagreement often signals measurement error. As instruments improve, discrepancies typically fade. Here, improvement amplifies confidence without dissolving conflict. The tension is no longer easily dismissed as oversight. It has become a feature of the data landscape. Precision has sharpened on both sides of the divide. Observations of the early universe, especially those derived from the cosmic microwave background, measured by the Planck mission, yield a tightly constrained expansion rate when interpreted within the standard cosmological model. The uncertainties are small, the statistical fits are strong, and the internal consistency is remarkable. On paper, the early universe picture looks complete. Meanwhile, local measurements have undergone their own refinement. Distance indicators have been recalibrated, systematics modeled more carefully, and independent teams have repeated the analysis. Observations using the Hubble Space Telescope and more recently the James Webb Space Telescope have reduced uncertainties in stellar distances and supernova brightness. Instead of drifting toward the early universe value, the locally measured expansion rate remains stubbornly higher. The error bars have narrowed. The gap has not. This is what makes the situation unusual. Typically, when two measurements disagree, improved resolution exposes hidden bias. An overlooked calibration error emerges. A subtle environmental factor is identified. A correction is applied. Convergence follows. In this case, refinement has deepened the divide. Each side now claims precision at the level of a few %. The statistical significance of the mismatch has climbed beyond what random fluctuation comfortably explains. The tension therefore shifts from being a technical puzzle to a conceptual one. If both sets of measurements are internally consistent and independently verified, then the disagreement may not reside in the data, but in the assumptions linking them. The early universe inference depends on a cosmological model extrapolated across billions of years. The local measurements rely on astrophysical calibrations anchored in present-day observations. The bridge between them is theoretical continuity. That continuity assumes the universe evolves smoothly according to well-tested equations. It assumes no hidden transitions, no subtle components influencing expansion in ways not yet accounted for. But the growing tension suggests that something within that chain may be incomplete. Either early conditions are being misinterpreted through an incomplete model, or late time measurements are revealing new physics not encoded in the standard framework. Importantly, this is not a chaotic disagreement. The data sets themselves are orderly. Residuals behave predictably. Cross-checks reinforce internal coherence. The discord emerges only when comparing across epochs. It is as if two precise clocks, built differently but designed to measure the same time, remain synchronized internally yet disagree when placed side by side. As measurement techniques diversify, the pattern persists. Gravitational lensing time delays, independent calibrations of supernovae, and alternative statistical analyses do not collapse the discrepancy. Some methods lean slightly one way, some slightly the other, but none erase the structural separation. Instead, the confidence intervals tighten around distinct values. In this sense, shrinking error bars function less like corrections and more like constraints. They fence in the possibilities. They reduce the space in which a trivial explanation can hide. The problem becomes harder, not softer. The range of acceptable theoretical adjustments narrows. Simple fixes strain against other well-measured features of the universe, from background radiation patterns to large-scale structure formation. Science often advances not when uncertainty is large, but when it is small and contradictory. The current expansion tension exemplifies the dynamic. It forces scrutiny not only of instruments, but of underlying principles. It asks whether the apparent coherence of the cosmological model is masking a subtle incompleteness. When error shrinks and tension grows, the data are not failing, they are signaling. Whether the signal points to overlooked systematics or to new physics remains unsettled. But the persistence of the discrepancy, sharpened by precision rather than softened by it, ensures that it cannot simply be ignored. The geometry of space. The universe appears spatially flat within tight margins. Flatness constrains total energy density. Altering expansion rates significantly would affect curvature measurements. Yet curvature remains near zero. Adjusting one parameter pressures another. The geometry resists dramatic correction. Spatial flatness is not a casual observation. It emerges from precise measurements of temperature fluctuations in the cosmic microwave background, most notably those obtained by the Planck satellite. Tiny variations in the background radiation encode information about the universe's large-scale curvature. The angles of primordial sound, wave patterns, act as geometric markers. If space were positively curved, those patterns would appear compressed. If negatively curved, they would stretch. Instead, they align almost perfectly with the expectations of flat geometry. Flatness implies that the total energy density of the universe, matter, radiation, and dark energy combined, sits remarkably close to a critical value. This balance is delicate. Even a small deviation would accumulate over billions of years, bending space in measurable ways. The fact that curvature remains near zero is not just aesthetically satisfying, it tightly constrains how much freedom cosmologists have when adjusting other parameters. The expansion rate, for instance, is not independent of geometry. In the standard cosmological model, increasing the present-day expansion rate while preserving early universe observations often requires modifying the composition of the universe. That can mean altering dark energy behavior, adding exotic early components, or tweaking the density of matter. But each change shifts the curvature balance. A universe expanding significantly faster today would typically leave a trace in the background, radiation's angular scale. This interconnectedness is what makes the problem so resistant to simple fixes. You cannot increase the expansion rate arbitrarily without disturbing the geometric consistency encoded in the microwave background. Attempts to introduce new early universe physics, such as a brief period of additional energy density, must be carefully tuned so they do not distort the observed acoustic peak structure. The geometry acts like a constraint equation, pushing back against dramatic revisions. Observations beyond the cosmic microwave background reinforce this stability. Large-scale galaxy distributions and gravitational lensing measurements independently probe curvature. The results converge toward flatness within small margins of error. The consistency across methods strengthens confidence that the geometry itself is not the source of the discrepancy. The space does not appear subtly curved in a way that could quietly reconcile conflicting expansion rates. Flatness also carries theoretical weight. Inflationary cosmology, the rapid expansion thought to have occurred fractions of a second after the Big Bang, naturally drives the universe toward spatial flatness. The success of this prediction has long been considered one of inflation's triumphs. Any proposal that significantly alters curvature risks undermining that coherence unless it provides an equally compelling alternative explanation. As a result, cosmologists face a balancing act. Adjust the expansion rate, and curvature constraints tighten, modify matter density, and structure formation prediction shift, tweak dark energy behavior, and the timing of cosmic acceleration changes. Each parameter is entangled with the others through Einstein's equations. The system is mathematically flexible, but observationally rigid. The geometry of space, therefore, functions as a stabilizing backbone for cosmology. It limits speculative freedom. It ensures that solutions to one tension do not cascade into broader inconsistencies. While this rigidity may seem frustrating, it also signals the robustness of the underlying framework. A loosely constrained model would allow easy reconciliation at the cost of predictive power. Instead, the near-zero curvature measurement forces any viable resolution to fit within narrow bounds. The universe's flatness is not merely a descriptive detail. It is a constraint that shapes every attempt to reinterpret expansion. As measurements grow sharper, geometry remains steady. The cosmos does not bend conveniently to accommodate discrepancy. Its structure holds firm, resisting dramatic correction and demanding explanations that respect its measured form. Time as a variable. Expansion rate is not static. it changes over cosmic time. If time itself were experienced differently across epochs, measurements might diverge. But the physics governing atomic transitions, light propagation, and gravitational interaction remains consistent in every observation. Time behaves uniformly within measurable limits. The expansion of the universe has never been constant. In the early cosmos, radiation dominated and expansion slowed rapidly. Later, matter took over, moderating the deceleration. In recent billions of years, dark energy has driven acceleration. This evolving rate is encoded in the equations of general relativity, first formulated by Albert Einstein. Time and space are intertwined within that framework, responding dynamically to energy and matter. Because the expansion rate evolves, one might wonder whether time itself could behave subtly differently across eras. If clocks ticked differently in the distant past, beyond the well-understood effects of relativity, then extrapolations from early measurements to present conditions could be skewed. A slight drift in how time accumulates might reconcile conflicting expansion values without requiring new energy components. Yet every available observation argues against such variability. Atomic transitions, which define our most precise clocks, produce identical spectral signatures across cosmic history. When we observe absorption lines from distant galaxies, the fingerprints of elements match laboratory measurements to extraordinary precision. The same quantum processes governing electrons in atoms billions of years ago appear unchanged. If time were flowing differently, in a fundamental sense, the spectral patterns would shift in ways we do not see. Light propagation also provides constraints. Photons emitted from distant supernovae stretch predictably as the universe expands. Their redshift corresponds exactly to the expansion history inferred from independent probes. The relationship between redshift and time dilation in supernova light curves confirms that distant events unfold more slowly by precisely the factor expected from expansion. The stretching of light and the stretching of observed duration align consistently. Gravitational interaction further reinforces temporal uniformity. Orbital dynamics in distant systems follow the same gravitational laws measured locally. The large-scale evolution of cosmic structure, simulated under constant physical laws, reproduces the filamentary patterns observed in galaxy surveys. Deviations in time behavior would ripple into structure formation, leaving signatures that current data do not support. The cosmic microwave background offers perhaps the most stringent test. Observations by the Planck mission map fluctuations, imprinted when the universe was only 380,000 years old. The timing of recombination, the moment electrons combined with protons to form neutral atoms, depends sensitively on atomic physics and expansion dynamics. The consistency between predicted and observed fluctuation scales suggest that time evolved precisely as modeled. Even alternative approaches to measuring expansion, such as gravitational lensing time delays, rely on stable temporal behavior. When light from a distant quasar is bent by an intervening galaxy, multiple images appear. Variations in brightness arrive at slightly different times due to differences in path length and gravitational potential. These delays match the expectations derived from constant physical laws applied across cosmic distances. There is no detectable drift in how time accumulates along those paths. This does not mean time is simple. Relativity already tells us it dilates in strong gravitational fields and at high velocities, but those effects are precisely calculable and universally confirmed. The question is not whether time can stretch, it clearly can, but whether its fundamental rate varies in a hidden, epoch-dependent way. So far, every test affirms consistency. If time were the hidden variable resolving expansion tension, its fingerprints would appear in atomic spectra, supernova durations, gravitational dynamics, or background radiation patterns. Instead, the evidence points to uniformity. Clocks separated by billions of light years agree within measurable limits. Time, then, behaves not as a shifting parameter, but as a stable axis along which cosmic history unfolds. The expansion rate changes, but the rules governing time's progression do not. Any explanation for divergent measurements must operate within that constraint. The universe evolves through time, yet time itself remains remarkably steady, the resisting reinterpretation as the missing key. Causality. Across scales, signals from distant galaxies take billions of years to arrive. You observe ancient states of matter. If unknown interactions altered expansion between then and now, their signatures should appear in structure formation. Simulations constrained by observation leave limited room for hidden transitions. Every photon that reaches a telescope carries a timestamp. Light from a galaxy 10 billion light-years away is not a picture of what is. It is a record of what was. This delay is not a limitation of measurement, but a feature of causality. Information propagates at a finite speed. Effects follow causes across space-time in ordered sequence. Because of that order, cosmic history is layered into the sky. If expansion changed abruptly at some point in the past, if an unknown field briefly dominated, or gravity behaved differently, those changes would not remain isolated. They would influence how matter clustered. Galaxies grow from tiny primordial fluctuations. Their distribution today reflects billions of years of gravitational amplification. Modify expansion, and you modify the rate at which structures form. Large-scale surveys reveal a web-like architecture of filaments, clusters, and voids. The statistical properties of this structure match simulations built under standard cosmological assumptions. These simulations evolve matter forward from the initial conditions measured in the cosmic microwave background, observed in detail by the Planck mission. Starting from those early fluctuations, computational models reproduce the clustering amplitude and scale seen in modern galaxy maps with impressive fidelity. This agreement constrains speculative transitions. An extra burst of expansion inserted between early and late epochs would suppress structure growth. A slower period would enhance clustering. Either effect would leave a measurable imprint in galaxy correlations, weak gravitational lensing patterns, and cluster abundances. Because these observables align closely with predictions, any hidden interaction must be subtle enough to avoid disrupting that coherence. Causality also operates through gravitational lensing. As light passes massive structures, it bends, tracing the intervening mass distribution. These distortions allow astronomers to map dark matter indirectly. The growth rate inferred from lensing measurements is consistent with the expansion history derived from background radiation and supernova data within known uncertainties. A dramatic mid-course correction in cosmic dynamics would echo in these lensing maps. Even the abundance of galaxy clusters across redshift functions as a chronometer. Clusters form from rare, high-density peaks. Their number at different epochs depends sensitively on how quickly matter can collapse under gravity against the backdrop of expansion. Observations of cluster counts across time place additional limits on any abrupt deviation from standard growth. This interconnectedness reflects a deeper principle. Cosmic evolution is cumulative. Small early differences compound over time. A modification inserted halfway through history would not remain confined to expansion alone. It would ripple into temperature fluctuations, matter distribution, velocity flows, and gravitational potentials. The sky preserves these cumulative effects. Simulations incorporate not just gravity, but baryonic physics, feedback from star formation, and radiative processes. While uncertainties remain in modeling small-scale details, the large-scale statistical behavior is robust. When constrained by observational data, these simulations leave diminishing room for radical departures in the expansion timeline. The allowed parameter space narrows as datasets improve. Causality therefore acts as both a guide and a constraint. It ensures that explanations must respect the chain of physical influence stretching from recombination to the present, and one cannot adjust a late time parameter without revisiting the entire evolutionary pathway that connects ancient photons to modern galaxies. The expansion tension invites creative solutions, but causality limits creativity. Any proposed hidden transition must tread a narrow path, strong enough to shift inferred expansion, subtle enough to preserve the observed architecture of the cosmos. So far, no candidate mechanism comfortably satisfies both conditions. Across scales, from atomic transitions to supercluster formations, the universe tells a consistent chronological story. Signals arrive late, but they arrive intact. Their coherence across billions of years reinforces a simple lesson. Cosmic history is tightly linked. Alter one chapter, and the rest must follow. The possibility of new physics. A persistent mismatch suggests incomplete theory. Perhaps a new particle species influenced early expansion. Perhaps gravity behaves subtly differently on cosmological scales. Yet each proposal must preserve the extraordinary success of existing models in every other tested domain. Additions must be minimal and precise. When discrepancies survive, improve measurement and cross-verification, theorists begin to consider extensions rather than corrections. The standard cosmological model has been remarkably successful. It explains the detailed structure of the cosmic microwave background, the distribution of galaxies, the abundance of light elements, and the accelerating expansion attributed to dark energy. Any proposed addition must fit seamlessly into this established framework without unraveling its coherence. One possibility involves additional relativistic particles in the early universe, sometimes referred to as dark radiation. A new light particle species could increase the early expansion rate slightly, altering how the cosmic microwave background encodes distance and scale. That change might shift the inferred, present-day expansion value without disrupting late-time observations. However, precision measurements from the Planck mission tightly constrain the number of such species. Even small deviations leave detectable signatures in the acoustic peak structure of the background radiation. The room for extra components is narrow. Another avenue considers early dark energy, a transient energy field that briefly contributed to cosmic expansion before fading away. If such a field existed, shortly before recombination, it could subtly modify the inferred scale of the universe at that epoch. Yet the timing must be exact. Too strong or too prolonged an influence would distort structure formation or alter the precise match between theory and observation in background anisotropies. The model must thread a fine needle, strong enough to ease tension, weak enough to remain nearly invisible elsewhere. More radical ideas question gravity itself. On cosmological scales, gravity governs expansion and structure growth. Perhaps general relativity, formulated by Albert Einstein, requires modification over vast distances. Slight deviations in how gravity propagates or couples to matter could shift expansion history without contradicting solar system tests. But gravity has passed experimental scrutiny with extraordinary precision across a wide range of scales. Gravitational wave observations, lensing measurements, and orbital dynamics reinforce its predictions. Any modification must reduce to Einstein's equations locally while diverging only subtly at cosmic scales. There are also proposals involving interactions within the dark sector. Dark matter and dark energy, though not directly observed, shape cosmic evolution. If these components interact weakly, exchanging energy over time, the expansion history could shift in ways not captured by the simplest model. Yet such interactions would influence structure formation patterns and cluster abundances, which currently align well with standard predictions. The difficulty lies not in imagining possibilities, but in constraining them. The existing cosmological model is tightly interlocked. Change one parameter and compensations must follow elsewhere. The background radiation, baryon acoustic oscillations, supernova luminosity distances, and lensing growth rates collectively act as cross-checks. A viable new physics proposal must satisfy all simultaneously. This requirement of minimalism is crucial. The goal is not to replace a successful framework with a speculative one, but to extend it carefully. Historically, physics advances through such refinements. Neutrinos were introduced to preserve energy conservation in beta decay. Dark matter emerged to explain galaxy rotation curves. Each addition solved the problem while preserving the broader structure of theory. The current expansion tension may represent a similar inflection point. It may ultimately dissolve under improved calibration, or it may signal a small but profound adjustment waiting to be discovered. If new physics is involved, it is unlikely to be dramatic. It would be subtle, mathematically precise, and deeply integrated with existing principles. A persistent mismatch invites bold thinking, but it demands disciplined restraint. Any extension must protect the predictive successes already achieved. The universe has revealed extraordinary coherence across epochs and scales. Whatever new ingredient might resolve the tension must respect that coherence, altering the cosmic story without rewriting its foundations. The cost of modification: introducing new physics to resolve tension risks, destabilizing the coherence already achieved. The standard model of cosmology fits vast data sets simultaneously. Alter one parameter carelessly, and concordance fractures elsewhere. The universe appears delicately balanced against revision. The current cosmological framework, often called the lambda CDM, did not emerge from a single observation. It crystallized gradually as independent lines of evidence converged. The temperature fluctuations mapped by the Planck mission align with predictions about early density perturbations. Supernova luminosity distances revealed accelerating expansion. Large-scale galaxy surveys trace structure growth consistent with cold dark matter. Each data set reinforces the others. The model's strength lies not in any one measurement, but in their collective agreement. This interlocking consistency means that theoretical adjustments are expensive. Suppose an additional early energy component is introduced to reconcile expansion rates. That addition would modify the sound horizon scale imprinted in the cosmic microwave background, but that same scale calibrates baryon acoustic oscillations observed in galaxy distributions. Change it in one context, and compensatory shifts must occur elsewhere. The parameters cannot move independently. Even dark energy, often treated as a simple cosmological constant, plays multiple roles. Its density influences the expansion timeline, which in turn affects structure formation and lensing signals. Replace it with a dynamic field, and you must re-evaluate cluster abundances, growth rates, and background anisotropies. A seemingly modest modification can ripple outward, altering predictions across epochs. Gravity itself exemplifies this fragility. General relativity, formulated by Albert Einstein, governs cosmic expansion as well as black hole, mergers, and planetary orbits. Gravitational wave observations confirm its behavior in extreme environments. If one proposes altering gravity on cosmological scales, that modification must remain invisible in solar system tests and consistent with gravitational wave propagation speeds. The parameter space for safe deviation is narrow. The coherence of lambda CDM is statistical as well as conceptual. Large datasets produce tightly constrained likelihood contours. These constraints overlap in ways that restrict flexibility. A shift large enough to erase the expansion tension may push the model outside acceptable bounds in another domain. The cost is not simply theoretical complexity, but empirical mismatch. There is also an aesthetic cost. The standard model achieves explanatory economy. With a small set of parameters, matter density, dark energy density, curvature, initial fluctuation amplitude, it describes a vast array of phenomena. Introducing additional fields, particles, or interactions increases dimensionality, while nature is not obligated to be simple. Unnecessary complication weakens predictive clarity. Each new parameter must justify itself by solving more than it disrupts. Historically, physics has advanced through both bold revision and disciplined conservation. Quantum mechanics overturned classical determinism, yet preserved conservation laws. The relativity reshaped space and time, while reducing to Newtonian gravity in appropriate limits. Successful revolutions respect prior achievements even as they extend them. The current tension demands similar care. The phrase "delicately balanced" is not rhetorical exaggeration. The near flatness of space, the precise scale of acoustic peaks, the growth rate of cosmic structure, each acts like a constrained surface. Deviations are permitted, but only within confined corridors. The universe tolerates little improvisation. This does not imply stagnation. It implies rigor. If modification is required, it must integrate seamlessly with the full architecture of observation. The challenge is to find an extension that resolves discrepancy without unraveling concordance. The cost of change, then, is proportional to the success already achieved. A model that explains little can be easily replaced. A model that explains much demands precision in any amendment. The universe appears balanced, not because it resists understanding, but because its measured consistency leaves minimal room for careless revision. The scale of consequence. A small shift in expansion rate affects estimates of the universe's age, size, and ultimate fate. Billions of years adjust lightly. Distances stretch differently. The timeline of structure formation recalibrates. A minor numerical gap propagates into profound structural implications. The Hubble constant is not merely a conversion factor between velocity and distance. It sets the scale of cosmic history. A higher present-day expansion rate implies a younger universe if extrapolated backward under standard assumptions. A lower rate implies greater age. Then the difference may appear modest, on the order of a few percent, but when applied across nearly 14 billion years, that percentage becomes hundreds of millions of years. Entire epochs subtly shift. Age is only the first layer. The observable universe's size depends on how rapidly space has expanded over time. A slightly different expansion rate modifies the distance light has traveled since recombination. That change alters the infrared radius of the observable horizon. Galaxies at extreme redshift would occupy slightly different comoving coordinates. The map of the cosmos stretches or compresses accordingly. This recalibration also affects structure formation. Galaxies did not appear instantly. They condensed gradually from primordial density fluctuations measured in the cosmic microwave background by the Planck mission. The rate at which small fluctuations grew into massive clusters depends sensitively on the balance between gravitational attraction and cosmic expansion. A faster expansion suppresses growth slightly. A slower one enhances it. Even a subtle adjustment shifts the predicted abundance of galaxy clusters across time. Supernova distances would be reinterpreted. The luminosity-distance relation used to infer acceleration depends directly on the expansion history. Modify that history and the inferred properties of dark energy change as well. A dynamic dark energy component might be required where a simple cosmological constant once sufficed. Thus, a local measurement discrepancy can cascade into a re-evaluation of cosmic acceleration itself. The consequences extend further into the future. The ultimate fate of the universe, whether expansion continues indefinitely, accelerates toward isolation, or evolves toward a different asymptotic state, depends on the precise interplay between expansion rate and energy density. A small present-day difference compounds over trillions of years. Long-term projections of galaxy separation and star formation timelines adjust accordingly. Even gravitational wave, standard sirens, independent probes of cosmic distance hinge on the expansion parameter. As detectors refine their reach, they will calibrate distances to merging compact objects across cosmological scales. Their interpretation connects directly to the same Hubble value. A persistent offset means their measurements will either reinforce one side of the tension or demand deeper revision. Philosophically, the scale of consequence underscores how tightly integrated cosmological parameters are. The expansion rate is not isolated. It threads through age, geometry, structure, and destiny. A difference of a few kilometers per second per megaparsec sounds technical, yet that technical difference reshapes the narrative arc of the universe. Historically, small numerical discrepancies have heralded major theoretical shifts. The precession of Mercury's orbit differed slightly from Newtonian prediction. The correction required general relativity, formulated by Albert Einstein. In that case, a minor anomaly opened a new conceptual horizon. Whether the current expansion tension carries comparable weight remains uncertain, but its reach is undeniably broad. The key insight is proportionality. In cosmology, small parameter changes scale over immense spans of time and space. Because the universe is vast and old, minor adjustments accumulate into large structural differences. What appears as a narrow, statistical gap becomes a redefinition of chronology and scale. Thus, the debate over expansion is not parochial. It touches the measured age of stars, the calibration of distant galaxies, and the trajectory of cosmic evolution. A minor numerical gap propagates outward, influencing every inference built upon it. In a universe governed by cumulative processes, precision matters profoundly. Human expectation of consistency. You expect nature to reconcile measurements because daily experience suggests consistency. On terrestrial scales, conflicting numbers signal error. Cosmology operates at distances and energies far beyond intuition. Consistency may exist, but not in the way you assume. In your everyday life, discrepancies are often trivial. A misaligned ruler, a misread thermometer, a clock set a few minutes off. Each conflict can be corrected, traced to an identifiable cause. You assume that repeated measurement will converge. This expectation underpins the confidence with which you interact with the physical world. You trust that a table has a single length, a kilogram is uniform, and a second ticks identically across the room. Cosmology, however, transcends such scales. Distances stretch billions of light years. Time spans billions of years. Forces interact in ways you cannot observe directly. When you measure expansion locally, using supernovae or Cepheid variables, you are constrained to the observable neighborhood of space and the present epoch. When you infer expansion from the cosmic microwave background, you are observing a snapshot 380,000 years after the Big Bang, then extrapolating across nearly the entire age of the universe. These are not merely different techniques, they are different contexts, linked by theory. Your intuition assumes that consistency is absolute. If two rulers produce different results, something is wrong. In the universe, measurements may each be internally consistent, yet incompatible when compared. The cosmic microwave background produces a stable, precise Hubble constant. Local distance ladders produce another. Both sets of data are reliable in themselves. Both are reproducible, calibrated, and cross-checked. The disagreement is not the result of sloppy measurement. It is a product of comparing measurements across regimes that do not align under current theoretical assumptions. This challenges human expectation. Consistency does not appear as a single value, reconciling all epochs. Instead, it appears as internal coherence within each observational framework. The early universe behaves consistently with its own internal rulers. The late universe behaves consistently with its own. But the two rulers do not agree when you try to extend one to the domain of the other. The cosmos exhibits order locally, yet global consistency is fractured across time and scale. Furthermore, the universe's evolution is cumulative and nonlinear. Small differences in initial conditions or in the interplay of energy components propagate into observable effects billions of years later. You cannot simply average measurements or assume they will converge. Nature's order is embedded in the dynamics of expansion, gravity, radiation, and dark energy. Each measurement is a reflection of that order, not a mirror of an intuitive expectation of agreement. even your concept of error is challenged. On Earth, discrepancy often signals inaccuracy. In cosmology, discrepancy may signal unrecognized structure, hidden parameters, or subtle interactions beyond your current model. Error margins shrink, yet divergence persists. The gap between early and late measurements does not vanish with refinement, it stabilizes. The universe does not bend to match expectation, yet it constrains the ways in which expectation can be applied. Human expectation also presumes linearity, that cause and effect unfold predictably, and that scaling a measurement across contexts preserves truth. Yet the universe is not linear in this sense. Cosmic history links epochs through complex interactions. Expansion, gravity, and structure formation are interdependent. Measurements at one time do not guarantee predictability at another. Ultimately, your instinct for consistency confronts a subtle truth. The universe may be internally consistent without being globally reconcilable in a single parameter. Observations are coherent within their domains, but those domains are separated by billions of years and light years. The expectation that nature will yield a single, neat answer is an artifact of human experience, not a requirement of reality. You are faced with a cosmos that is orderly and yet not intuitively unified. Its rules persist across space and time, but the projection of those rules into a single number, one expansion rate, fails. The discrepancy is not disorder. It is a deeper structural tension between what is measured and what is assumed. Your expectation of absolute reconciliation is a terrestrial habit, one that does not scale to the universe itself. Data without narrative. The measurements themselves are neutral. They do not explain their divergence, they simply persist. Interpretation attempts to bridge them. The numbers remain indifferent. They agree locally, they disagree globally. Each dataset tells a story only about its own domain. The cosmic microwave background encodes early universe conditions with extraordinary precision. Its fluctuations trace density contrasts, sound horizons, and the expansion rate at recombination. Within this framework, the numbers are coherent. They form a narrative of an expanding universe whose properties evolve predictably from a hot, dense beginning. Local measurements, by contrast, record the behavior of the universe at much later epochs. Cepheid variables and type 1a supernovae are calibrated carefully, distances measured with painstaking cross-checks. The resulting expansion rate reflects present-day dynamics, constrained by observed luminosities and velocities. Within their context, the data are internally consistent. They form a narrative of an accelerating universe that agrees across independent themes and techniques. The divergence arises only when these narratives are compared. The cosmic microwave background predicts a Hubble constant lower than that measured locally. Each measurement remains valid in its own regime. Neither is in error according to its internal logic. Yet when projected across billions of years, the numbers cannot be reconciled without invoking adjustments to either theory or underlying assumptions. The data themselves remain neutral. They neither require nor justify a particular explanation. Efforts to construct a single narrative involve connecting observations through cosmological models. The standard model, lambda CDM, serves as a bridge. It translates early universe physics into predictions for late-time expansion. But tension arises because the model cannot fully reconcile the two sets of measurements without introducing subtle modifications. New parameters, transient energy components, or slight deviations in fundamental constants have been proposed, each intended to produce agreement. The data, however, remain indifferent to these interpretive attempts. This indifference is profound. Observations do not bend toward human expectations. They do not smooth over inconsistencies in the hope of a unified story. Each measurement is an account of reality at a particular scale and time. Their persistence in divergence forces recognition that the cosmos may resist narrative simplification. The universe is not obligated to produce a single, cohesive value for expansion. It only obligates itself to be measurable and consistent within each observational regime. Moreover, the neutrality of data highlights the role of interpretation. Statistical methods, model assumptions, then parameter fitting attempt to weave measurements into coherent histories. Analysts impose continuity across epochs, connecting early and late universes through physical laws. These interpretations rely on human reasoning and theoretical constructs. They are attempts to generate narrative coherence, where the raw numbers offer none. The gap between predicted and measured expansion rates is a reminder that narrative is human, not intrinsic to the data. Even as measurements grow more precise, the gap persists. The uncertainty shrinks, yet divergence solidifies. Data do not converge simply because observation improves. Precision amplifies clarity without resolving incompatibility. The numbers enforce their neutrality. Agreement is found within, but not between, domains. This separation extends beyond expansion rate. And other cosmological parameters, such as matter density, dark energy fraction, or structure growth rates, follow similar patterns. Measurements are internally consistent, but can produce tension when combined globally. The universe conveys information accurately within each context, yet resists a single, overarching story that reconciles all epochs effortlessly. Ultimately, the data exist without narrative. They describe, they constrain, they challenge interpretation. They do not justify theoretical preference. Their persistence in divergence is a quiet statement. The cosmos is indifferent to human attempts to craft a seamless story. Understanding must accommodate this neutrality. You can interpret, model, and theorize, but the numbers themselves remain unyielding. They agree locally, they disagree globally, they simply exist. The silence in public discourse. Outside scientific literature, the tension receives limited attention. It is neither catastrophic nor easily explained. It sits in technical papers, statistical analyses, conference discussions. Its persistence is acknowledged. Its resolution remains uncertain. This silence is not the result of oversight. Cosmologists are acutely aware of the discrepancy. Each new measurement, each improved calibration, is carefully analyzed. The statistical significance of the divergence is calculated rigorously. Researchers present findings with full transparency in peer-reviewed journals. Yet the broader conversation rarely reaches popular media. The topic is technical, abstract, and lacks immediate, dramatic consequences. It does not threaten safety, nor does it provide a simple narrative of discovery or crisis. The tension exists in the space between precision and understanding. The Hubble constant, measured from early and late universe probes, disagrees by a few kilometers per second per megaparsec. On human scales, this difference is negligible. Across cosmic distances and times, it accumulates into profound implications for the universe's age, size, and expansion history. Still, these subtleties resist intuitive storytelling. Translating them into headlines or sound bites risks oversimplification or misrepresentation. Within the scientific community, the conversation is active but cautious. Conferences host sessions dedicated to the Hubble tension, where teams present increasingly refined measurements and theoretical proposals. Papers explore early dark energy, dark radiation, and potential modifications of gravity, each evaluated against a web of constraints from cosmic microwave background, large-scale structure, and supernova data. The discourse is meticulous, analytical, and deeply technical, yet these deliberations rarely enter public consciousness. Part of the silence stems from uncertainty. No proposed resolution is universally accepted. Modifying early universe physics may improve agreement with local measurements, but risks disrupting the concordance elsewhere. Adjusting the properties of dark energy or postulating subtle new particles requires extreme precision to avoid contradiction with well-established observations. Because the solutions are constrained and often mathematically subtle, the field lacks a definitive breakthrough to announce. Another factor is cultural. Cosmology values restraint. Bold claims without rigorous support are treated with skepticism. Journals and conferences emphasize careful reasoning over speculation. Scientists communicate the results clearly within the field, but often avoid overstatement in public forums. The tension is real, but it is not yet a problem that can be resolved with certainty. Public attention, when drawn to unresolved issues, risks misrepresenting the measured and verified nature of the findings. The silence also reflects the character of the tension itself. Unlike anomalies in laboratory physics, where an experiment can be repeated under controlled conditions, cosmology deals with a singular universe. You cannot rerun the Big Bang or observe a second cosmic microwave background. Observations are constrained by light travel time, distance, and the availability of precise instrumentation. The inability to experiment in the traditional sense makes the tension abstract, reinforcing its quiet presence rather than dramatic visibility. Despite the muted public discussion, the scientific record preserves the tension in detail. Every new measurement is logged, every methodology documented, every statistical analysis scrutinized. In the quiet of papers and conference talks, the discrepancy is acknowledged repeatedly. The expansion rate tension is neither ignored nor dismissed, it is simply unresolved. Ultimately, the silence in public discourse does not equate to ignorance or neglect. It reflects the technical nature of the problem, the need for careful interpretation, and the absence of a conclusive resolution. The universe continues to expand at rates that are internally consistent, yet globally discordant. Researchers observe, measure, refine, and theorize. Outside the field, the tension remains quietly unspoken, a subtle reminder that our understanding of the cosmos is both precise and incomplete, a universe that almost aligns. The remarkable feature is not failure, but near success. The model nearly unifies early and late measurements. The disagreement is small relative to cosmic scale. Yet small inconsistencies in fundamental constants cannot remain indefinitely unresolved. The standard cosmological model, lambda CDM, has demonstrated an extraordinary capacity to describe the universe across space and time. From the physics of the first few minutes after the Big Bang, when light elements formed, to the large-scale structure of galaxies today. However, the model reproduces observations with remarkable fidelity. Its parameters, matter density, dark energy fraction, curvature, and the amplitude of primordial fluctuations interlock to produce predictions that align with an extraordinary range of phenomena. The divergence in the expansion rate, although statistically significant, is tiny compared to the vastness of the cosmos. A few kilometers per second per megaparsec may seem negligible in daily terms. Across billions of light years, it produces differences in age, distance, and expansion history, yet these remain within a narrow envelope. It is a testament to the underlying model that even with this discrepancy, the universe remains almost entirely predictable. Most measurements and simulations continue to match observation. The cosmic narrative is coherent in nearly every respect. This near alignment highlights the stability of physical laws. The fundamental constants, such as the gravitational constant, the speed of light, or the fine structure constant, define the behavior of matter and energy across cosmic history. Slight mismatches in inferred expansion rates hint at tensions in these constants when applied across regimes separated by billions of years. Even small inconsistencies have consequences. They ripple into the interpretation of structure formation, cluster evolution, and cosmic chronology. It is also striking that most parameters agree to extraordinary precision. The density of baryonic matter inferred from the cosmic microwave background matches the abundances of light elements. The flatness of space, observed across multiple surveys, remains consistent with theoretical expectations. Galaxy clustering statistics and weak lensing measurements align with predictions derived from early universe conditions. The model succeeds in nearly all domains, reinforcing the sense that the mismatch in expansion is a subtle anomaly, not a fundamental failure. The tension is therefore a window into the limits of understanding, not a collapse of theory. It suggests that the universe is operating under rules that are largely captured, but not fully resolved, by current models. The discrepancy invites scrutiny of assumptions about early universe physics, dark energy, and potential hidden interactions in the dark sector. Any resolution must preserve the integrity of the existing successes, meaning that new physics cannot disrupt the precise matches observed elsewhere. From a philosophical perspective, this almost alignment emphasizes the delicate balance of cosmic parameters. Nature maintains internal coherence, even while permitting small deviations that signal unknown structure. These deviations are not random. They are constrained, persistent, and reproducible. They hint at a deeper pattern that has yet to be fully interpreted. The challenge is methodological as well as conceptual. Observational precision continues to improve, narrowing error margins and amplifying confidence in both early and late measurements. As these numbers stabilize, the tension becomes more pronounced, even as the universe's general behavior remains highly predictable. The near success makes the remaining inconsistency more compelling. The universe is close to fully described, yet that final fraction resists explanation. Ultimately, a universe that almost aligns is both reassuring and unsettling. It confirms that our theories capture the vast majority of cosmic behavior, but it also demonstrates that even minor numerical tensions carry weight. Small mismatches in fundamental constants or expansion rates are not trivial. Over cosmic distances and times, they imply subtle structural divergences, affecting chronology, scale, and evolution. The near unity of the model underscores the precision of current understanding, while simultaneously emphasizing the incompleteness of that understanding. The universe is precise, coherent, and nearly predictable. Yet it preserves a small, persistent gap, an open question encoded in the very constants that govern its evolution. The almost alignment is a testament to human insight, a marker of scientific success, and a signal of mysteries that remain just beyond reach. Precision as a double-edged tool. The more precisely you measure reality, the narrower acceptable explanations become. Precision eliminates flexibility. It confines interpretation. As error bars shrink, theoretical freedom contracts. The tension becomes sharper, not broader. Precision in cosmology is extraordinary. Satellites such as Planck map the cosmic microwave background with microkelvin sensitivity. Space telescopes resolve Cepheid variables across millions of light years. Gravitational lensing surveys chart subtle distortions in galaxy shapes. Each measurement comes with rigorous uncertainty quantification. The numbers are not approximate. They are reproducible, cross-checked, and constrained. Each decimal point carries significance. This exactness, however, is a double-edged tool. In the past, broad error margins allowed multiple interpretations. A slight discrepancy could be dismissed as statistical noise. The universe could wiggle within uncertainties, permitting theoretical flexibility. Now, with error bars reduced to fractions of a percent, the room for adjustment vanishes. Any proposed explanation must thread a narrow path between constraints. Precision confines models. It demands that modifications be minimal, targeted, and internally consistent. The Hubble tension illustrates this constraint. Early universe measurements yield a precise expansion rate. Local measurements yield another, equally precise rate. Both sets are internally robust. The overlap of uncertainty is minimal, yet disagreement persists because the measurements are highly constrained. The hypothetical solutions cannot be arbitrary. Introducing a new particle species or modifying dark energy dynamics must reconcile the tension without disturbing the exacting agreement observed elsewhere. One misstep would produce observable contradictions in the cosmic microwave background, baryon acoustic oscillations, structure formation, or lensing statistics. In essence, precision acts as both a spotlight and a cage. It illuminates discrepancies with clarity, highlighting tension that was previously hidden, but it simultaneously restricts the freedom to reinterpret or manipulate models. Every additional digit in measurement translates into a reduced parameter space for theory. The universe permits no loose adjustments. Even a subtle modification must satisfy a web of interdependent constraints stretching from recombination to the present epoch. This has philosophical implications. Human intuition often treats uncertainty as opportunity. Greater precision is assumed to simplify understanding. In reality, it may amplify unease. The more we know, the less room there is for explanatory compromise. Where once a rough estimate could be reconciled with a flexible model, now the same estimate confronts theory with unavoidable conflict. The tension is no longer a statistical curiosity. It becomes a concrete challenge to the completeness of existing frameworks. Precision also sharpens the temporal dimension of constraints. Expansion is not static. Historical epochs, from the first light to galaxy formation, are connected. Every precise measurement at one epoch constrains interpretation at others. The cumulative effect is that even minor discrepancies propagate backward and forward in time, reducing tolerance for error. The entire cosmic history is interdependent, and precision compresses the latitude within which theories can vary. Finally, precision transforms the interpretive landscape into a landscape of paradox. The Hubble tension is a product of exactness. The data agree internally, yet disagree when compared across epochs. The conflict is not an artifact of measurement error. It is a reflection of reality as observed. The sharper the measurements, the clearer the disagreement becomes. It is a signal from the universe that our models, however successful, may be incomplete. Thus, the precision is not merely a technical improvement, it is a revelatory force. It confines, constrains, and demands rigor. The sharper the instruments, the more inescapable the tension. What was once a soft discrepancy becomes a precise anomaly. Each decimal point reduces interpretive freedom, emphasizing that the universe does not bend to expectation. Precision clarifies not only what we see, but also what we cannot easily reconcile. The very act of measuring with exactness exposes the narrow corridors through which theory must pass. The question that remains: if two independent methods measure the same expanding universe, and both are correct within their frameworks, then either an unseen mechanism links them, or a foundational assumption is incomplete. The universe does not openly contradict itself, yet your measurements do. The numbers align internally, they diverge collectively. The question remains whether reality is subtly more complex than the model that almost explains it, or whether the act of measuring across cosmic time introduces a distortion you have not yet recognized. The dilemma arises because each measurement is a reflection of a different temporal and spatial regime. Early universe probes, like the cosmic microwave background, capture conditions just 380,000 years after the Big Bang. They encode density fluctuations, sound horizons, and expansion rates in a snapshot that has traveled across billions of years. Late universe probes, such as Cepheid-calibrated supernovae, sample the universe as it exists today. Both methods are internally consistent, yet their extrapolations do not converge. The one possibility is that an unseen mechanism connects these regimes. Perhaps a subtle energy component acted briefly in the early universe, leaving measurable consequences only at later times. Early dark energy is one such candidate, proposed to reconcile the observed expansion rates. If it existed, it would have influenced the expansion history just enough to shift predictions without disrupting the otherwise precise agreement between theory and observation. But any such mechanism must be narrowly constrained. Too strong, and it violates the cosmic microwave background or baryon acoustic oscillation data. Too weak, and it fails to resolve the tension. Alternatively, the discrepancy may point to incomplete understanding. Foundational assumptions, such as the uniformity of physical constants, the simplicity of dark energy, or the unmodified behavior of gravity on cosmological scales, may conceal subtle complexities. Gravity, for instance, is tested with extraordinary precision locally, yet its behavior across vast cosmic distances remains comparatively uncharted. A minute deviation in gravitational interaction over billions of light years could manifest as the tension you observe. Similarly, unknown interactions within the dark sector could redistribute energy or influence expansion in ways that are measurable but remain unmodeled. There is also the question of measurement itself. Observing the universe across time is not equivalent to repeating an experiment in a laboratory. You cannot rewind cosmic history. Light from distant galaxies carries information from epochs long past, yet your instruments and interpretation impose frameworks that may subtly distort that information. Calibration, distance ladders, and statistical modeling are remarkably robust, but they are not immune to systematic effects that emerge only when observations are combined across epochs. The divergence may therefore reflect an inherent challenge in translating measurements into a unified picture. The persistence of this question underscores the delicate balance of cosmological models. The lambda-CDM framework succeeds across countless phenomena. Its predictive power is vast, yet its near success amplifies the significance of small mismatches. If the model were failing entirely, discrepancies would be obvious, sprawling, and easily attributed to error. Instead, the universe almost aligns, and the tension remains narrow but irreducible. The precision of your measurements, combined with the model's overall success, isolates a subtle misalignment that demands explanation. Philosophically, this question is unsettling because it sits at the intersection of observation and assumption. The universe is not chaotic. It follows consistent laws. Yet the act of measuring, projecting present techniques backward or forward in time, reveals gaps in understanding. Reality may be more complex than your current framework suggests, or the process of translating light and motion into a single expansion value may inherently introduce distortion. Either interpretation points to limitations in your grasp of cosmic structure. Ultimately, the question that remains is open-ended. It is neither a flaw in instrumentation nor a failure of theory alone. It is a consequence of pushing precision and scope to their limits. The universe has presented a subtle divergence, internally consistent yet globally unresolved. Understanding may require new physics, revised assumptions, or an unrecognized systematic, but it may also require a fundamental reconsideration of how measurement itself interfaces with cosmic history. You are left with numbers that coexist without agreement. They are correct within their domains. They refuse to converge collectively. The question persists quietly across billions of years and light years. Is the universe more intricate than your models? Or is measurement itself a lens that reshapes the apparent truth? Either possibility forces recognition that cosmological understanding, however precise, remains incomplete.